Hey there, welcome back to Short Takes 331. Today we continue to build towards quantum Monte Carlo, and I want to tell you about something called the trace-determinant identity. So in fact there's several of those, so we're going to talk about these in this part today, and there's going to be a second part and maybe even a third part. So far in our journey towards finite temperature quantum Monte Carlo, we've talked about the grand canonical partition function. Here our Hamiltonian has the kinetic energy part and an interaction. And one thing we did was that we took this exponential of minus beta h, which I try to convince you is a complicated object because the Hamiltonian is made out of these two parts that don't commute with each other. And we factorized that into n tau factors in this way, where tau is some parameter. Typically, tau will have the same units as beta, the inverse temperature, and tau will be an integer. And so we're doing this in an exact fashion. So this is just taking powers of e to the minus tau h to build up to e to the minus beta h. And each of these small factors, if you want, assuming that tau is a small parameter, which means that n tau is large in some sense, each of these factors can be factorized further using the Trace-determinant decomposition. And that was our episode 1 in this series on toward quantum Monte Carlo. And this is the simplest type of Trace-determinant factorization you can use, e to the minus tau t, e to the minus tau v, so kinetic factor, potential factor, but you can make it much more complicated. And here I use an equal sign, but of course this is not exactly equal. There's an error here that we're making when we're approximating this left-hand side with the right-hand side. So there are definitely much better decompositions than this one. Here I'm using this one just for brevity. And then we take this one, which is the complication, the part where that contains the interaction, and we used we used the Haber-Satonovich transformation to write this part as an integral, a field integral, a complicated integral I mentioned last time of the exponential of a one-body operator. And so we have something simple here, something we hope to do with Monte Carlo, and then the result of doing that integral is the interaction exponential factor that we need for our Trace-determinant decomposition, which we need to build e to the minus beta h, which we need to get our thermodynamics. And so this is how we're building this. Now, last time I introduced all those steps, and or at least the last two times I introduced all those steps. Last time was just about Haber-Satonovich, but at the end of that discussion, I used but did not prove that the Fock trace, the grand canonical trace of e to the a, e to the b, e to the c, where all these are one-body operators, is the determinant of 1 plus the exponential of the single particle representation of those operators. So here a, b, and c are the single particle representations of the operators a, b, c, etc. respectively. So what that means is that if we specify a single particle basis here, so a basis of single particle states, then the A is a matrix of elements aij sandwich state between state I and j, the operator A that we have over here. Now, by the way, this is assuming that these operators are all fermionic operators, so that our particles in our system, the particles that we're interested in calculating the thermodynamics over here, they're all fermions. So if we have bosons instead, this will be a little different. So for now, I'm focusing on fermions, but we will generalize it to bosons later, and I'll tell you what it looks like. So today what I want to talk about is the proof of this trace-determinant identity. This looks really, really weird. If you're familiar with linear algebra at all, you know that traces and determinants are things that are extremely different. They really don't talk to each other at all normally. So what's going on here? How does this make sense? Part of the trick behind this is that this trace is a trace over a space of multi-particle states, and this determinant is a determinant of a different space entirely. So it's a determinant over only the single particle representation of these operators here. And so that's why there's something going on here that really it's a matter of notation, if you want, or a matter of the fact that this trace is not a trace over the same space where this determinant operates. So let's talk about that. So to prove this, we start with the simplest possible case. As always, whenever you have to do a proof and you don't know what you're doing, I recommend start with the simplest possible case and take it from there and see what you can do building on that. So let's consider the case where we only have e to the a, so just one factor in this big trace of products of one body or exponential of one body operators. So that trace of e to the a, we claim according to this theorem that it's the determinant of 1 plus e to the a. And so our A operator here is one body operator. That means that by definition, it takes this form. So here are the matrix elements in its one-body representation, the single particle matrix elements, and we're going to call these Aij as above, as here. And then we have here the creation and annihilation operators that accompany this one-body operator. So this is just a definition. This is a completely generic one-body operator. And since these are fermions, as we're assuming, then this A dagger A anti-commute. They obey this anti-commuting algebra property. So the anti-commutator of A with A dagger is delta Ij. And so here this means that A dagger minus A dagger A is delta Ij. So it's 1 if I is equal to J and 0 otherwise. If this were bosons, we would be talking about a commutator algebra and not an anti-commutator algebra. So again, this is A dagger plus A dagger A. I might have said it wrong just before. So this is A dagger plus A dagger A is delta Ij. That's the anti-commutator. So the commutator algebra would be A dagger minus A dagger A, and that would be for bosons. But for now, we're focusing on fermions. The next thing we want to do is we want to diagonalize A, or if you want, we want to represent A in terms of its diagonal equivalent matrix. So we're assuming here that A can be diagonalized by unitary transformation. This is typically true if A is what's called a normal matrix. And so we proceed assuming that. And so A will have this, if you want, this spectral decomposition where we have a unitary matrix, or here a unitary matrix, it's dagger, and D is a diagonal matrix that will take this form. So the elements of D are diagonal elements, the only non-zeros, and we have D1, D2, and so on, and off diagonals are all zeros. And so I'm going to go ahead and insert into where we had the elements Aij, this U dagger Du Ij matrix element. And so after rearranging some of these elements here and using the fact that U dagger Du is a product, and using the sum over K to represent that product, I can rearrange and put the A dagger to the left, U dagger here, DK stays in the middle, and then UKJ A dagger, AJ from here all the way to the right. And so what we're going to use this stuff, all this product somewhere I, that's the only part where I appears, to represent or to invent a new operator BK. BK dagger. This is BK dagger. And then this one here, we're going to go ahead and take all this. The only place where J appears is here. And we're going to use that to represent the BK, or to invent a new BK operator. These operators, BK and BK dagger, are unitary transformations of A dagger and A. So I missed some hats here, but these are operators, and these are unitary transformations of A and A dagger. And because they're unitary transformations, they obey the same commutation relations, or anti-commutation relations. So what that means is that the BKs are just as the A's, they're fermionic operators. But what we gain here is that instead of having two sums over I and J with matrix elements Aij and A dagger A, Ij, we have just one sum over K, BK dagger, DK, BK. And so with that result, it's much easier to take the exponential of A, which is what we're interested in. So we're interested in taking the exponential of A, and we want to take the trace of that. So with this result, working in the basis where A is diagonal, then we can go ahead and write e to the A as a product over all K's of e to the DK, BK dagger, BK. So this product comes from this sum, of course, taking the exponential of that. Now, it turns out that this BK dagger BK, because of the anti-commutation relations that we have here, you can show, it's not hard to show at all, that BK dagger BK squared is BK dagger BK. So the square of this operator is itself. And that means that it can only take, that means that there are two properties actually. So for any operator such that the square is itself, first of all, the exponential of their operator is always going to be 1 plus e to the c, here c is just some constant, minus 1 times the operator. And you can show that very easily by doing a Taylor expansion of this operator. And you'll find that there's no power greater than the first power of O that appears, and it appears with this coefficient e to the c minus 1. And so that's one property. And the other property is that because O squared is O, the eigenvalues of O can only be 0 or 1. There's nothing else. This represents, of course, the fermionic property of the system. So BK dagger BK is an occupation operator for state K in our transformed basis. And so that state can be either unoccupied, in which case the eigenvalue is 0, or it can be occupied only once by our fermions. And so the eigenvalue has to be 0 or 1. There's nothing else. And we'll use that in just a minute But for now, this first property is used here. So the exponential of this operator is just 1 plus e to the dk. Dk is just constant here, minus 1 bk dagger bk. And we get to do that for each of these factors, for all k's. And so we have this product still, but now we have it in this form. So this is much better. It's much better than the previous one because now the bk dagger bk doesn't appear in the exponent. It just appears down here. So that's nice. Now we're in a better position to take the trace. This grand canonical Fock space trace of e to the a is the sum over all possible quantum numbers k1, k2, and so on that appear in this factor, and of a state made out of this product k1, k2, and so on. These are single particle states representing the possible occupations that you can have for the various single particle states, and then the same on the right. So remember, we're taking a trace, and now what will happen inside this product is that there's going to be a k1 factor, a k2 factor, a k3 factor, and so on and so forth. This k1 all the way on the outside will only catch b1, b dagger 1, b1. k2 will only catch b dagger 2, b2. So each of these factors in this product gets one of these sandwiches, one of these brass and cats that sandwich this factor. That's what it is. And when that happens, you sum over these k1s and occupation numbers, and all you can have is 0 or 1, because we have that the eigenvalues of the operator bk dagger bk can only be 0 or 1. And so what we get then when we sandwich with k1, for example, the term that has b1, is that we get when the eigenvalue is 0, we get the 1, and that's this 1 over here. And when the eigenvalue is 1, we get that the 1 cancels with this 1, and we get just e to the d sub 1. And so that's this term here. So that happens for k1. It happens again for k2. Once again, k2 will sandwich only b2 dagger b2, and with k2 on the other side. And that k2 can only be 0 or 1. That's the occupation of that state labeled 2 in our single particle basis. And so that eigenvalue of b2 dagger b2 can only be 0, in which case we get a 1, or it can be 1, in which case the 1 cancels with the 1, and we get e to the d2, and that's this factor here. And so we continue like that all the way to the end, where our basis ends, or all the way to infinity if our basis is infinite. And the result of that is that you get the product of 1 plus e to the d1, 1 plus e to the d2, and so on and so forth, which is of course just the determinant of 1 plus e to the d, because remember, d is our matrix that is diagonal. If we go up here, d is a matrix that is diagonal, and this way zeros everywhere else, and on the diagonal we have d1, d2, d3, and so on. And so that's exactly what you would expect to get from the determinant, and that's why we have a connection between the trace here, the Fock space trace, and the determinant. Now, one last step is that this e to the d is unitarily equivalent to e to the a, and so we're allowed to replace then e to the d with e to the a, and so we have that this determinant is equal to this determinant. And then you have then the first part of the proof, that the trace of e to the a operator, where a is a one-body operator with matrix elements a, then in single particle space, then it's equal to the determinant of 1 plus e to the a. Now that's one factor case. So that's a case where we only have just one factor e to the a operator, and we want to take the trace of that. So then how do we proceed beyond that? What about e to the a, e to the b? In that case, we're going to follow a completely different approach. So you'll be tempted when trying to prove this for more than one factor to say, well, maybe I should diagonalize both, but typically a and b will not commute, and so you can't diagonalize both simultaneously. And so diagonalization is really not an answer here. The answer is algebraic. What you have to do is to go ahead and use this famous formula called Baker-Campbell-Hausdorff, and sometimes attributed to more people as well. I'll call that sometimes BCH. So you'll use BCH to turn e to the a, e to the b into e to the z. So the BCH formula will tell you what z is. So how to take the logarithm, if you want, of e to the a, e to the b. And once you have this z operator, then you apply part 1, because you turn the two factors into one factor, and we're in the context then of the first part of this theorem. Now it turns out that this z operator is actually takes this form, sum of ij of our usual factor a dagger I, a, j, but this matrix element that goes in between is itself the logarithm of e to the a, e to the b. And so the exponential of e to the z, or the exponential of z. So e to the z is just e to the a, e to the b. So in other words, this operator z hat here has a representation such that e to the power of its matrix, one-body matrix elements, is actually the product of the exponentials of the one-body matrix representations of a and b respectively. And so so basically what that means is that you're in fantastic shape to go ahead and apply this theorem, but now with more than one factor. So I'll spell that out in more detail in part 2 of this sub-series of the series toward quantum Monte Carlo, determinant, trace determinant identities. So there'll be a part 2 to this, but you can see, you can sort of see already that if this e to the a is such that my operator a is the logarithm of this, then when I take the exponential of my z, in other words, when I write this down, then I'm going to get e to the a to the b, which is exactly what I wanted for proving my theorem. And that's about all I have for you today. Once again, there's going to be a second part to this where I will tell you in more detail how this whole section works out to prove our more general case. And then I'll tell you how things work out for the bosonic case. And then we'll talk about some other related details between fermions and bosons. I hope you enjoyed this video. If you did, please consider liking and subscribing to the channel. It really help us. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, maybe I can help you. You can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below. And I'll see you next time.